All right. One of the things we tell you with the third law is that, no force exists in isolation. So we can actually demonstrate that very nicely without contact, showing you two objects that have magnets on them. These carts have magnets on the end of them. So if I try to push them close, I get actually a lot of resistance here. And I actually don't want to put them in contact with each other. I just want to bring them close together so that they can kind of push off each other nicely. So if I let go at the same time, you're going to watch them move away from each other. So that is the third law in action. And what you see is that one is exerting a magnetic force on the other, but at the same time, it occurs for both of them. So it's essentially like I have two magnets here. And when you put two identical poles up to each other, they repel one another. So what we get is that if this is object number one and this is object number two, you get F1 on 2 here, F2 on 1 there, and as soon as I let them go, what you're going to see is the resulting motion of the two. And because their masses are identical to each other, we see them moving off essentially with the same speed in the end. So the second law is pretty easy to analyze for two objects like this. Now, let's say for the sake of example, this mass is 0.25 kilograms and this mass is 0.25 kilograms. So we got M1 and M2 here. Essentially, we can apply the second law to this if we happen to know what the forces are. Let's just, for the sake of argument, say that there's a 20 Newton force acting on it, which would, by the third law, make this also 20 newtons. They have to apply identical forces to each other in opposite directions. Once you know that, you can simply do the second law of the net force equaling mass times acceleration. And when you do that, it's pretty easy because we only have to look at the one force acting on the object here. So you got 20 newtons here, a mass of 0.25. This is A. 20 divided by 0.25 would give us our acceleration. And if that were a legit number, I probably severely overestimated that force. I would get 80 meters per second squared. You know what? Let's make it 2.0 newtons just to make it more realistic. Then that would only give me about 8.0 meters per second squared on my acceleration. And then you would find that you could do the same calculation here, but that would be kind of redundant since it does have the same mass and you get the same acceleration as well. However, if the masses are mismatched, that number would change and you would get a different acceleration. Now, another example of the third law in action, which isn't as obvious, is one mass moving another. So what I'm going to do is, actually, I'll take two identical weights here. Two 200-gram weights. What I could do is I could push them, and when I push them, they will both move in the same direction with the same acceleration. They move in unison. So if we think about what's happening here, I've got two masses here. They are both 0.2 kilograms, and they're in contact with each other. And what I did was I pushed it myself. I applied a force to this mass here. So let's give this thing a, let's say it's an 8 Newton force to the right, acting on this object. Now, I'm not touching this object. I'm not in contact with the other mass, yet it moves. It's moving because this mass is doing the pushing here. So we might as well call these object 1 and 2 to differentiate them. And essentially, I'm going to draw my diagrams of the forces acting on them separately. So I've got object number 1 here, object number 2 here. And what I know is that I applied an 8 Newton force to the right on this object. However, they both end up moving. And it's not me that pushes object number 2, it's object 1 that pushes object number 2. So I'm going to call this force of 1 on 2, F1 on 2. And that would explain why this object would move to the right. Now, according to the third law, if one object exerts a force on another, the other object must exert the force on it, but in the opposite direction. So if 1 pushes 2, I expect 2 to push 1 back. And we're looking at those values, and it doesn't quite make sense as to why that would move until you actually figure out what the numerical value of that is. So, realistically speaking, the way to approach getting the acceleration here would be, let's pretend that there are a combined mass of 0.4. And then if I have simply an 8 Newton force acting on that, it's pretty easy to get our acceleration. I would just use the second law, and I would do net force equals ma. With a net force of 8, a mass of 0.4, and that would give us our a value. So 8 divided by 0.4 gives me an acceleration value of 20 meters per second squared. So they'll both move in unison while I'm pushing with that particular force. Now, that being said, we can now take the second law and apply it to an individual mass and figure out what that force is acting on it. Because keep in mind, we have no idea what that force is. So if I do the net force over there, what I'm going to get is the same starting formula, but I don't know what this force is. I do know that the net force has to be equal to F1 on 2, because that's the only force we're really looking at here. And then the mass of it is only 0.2 now, and we know our acceleration is 20 because we determined that there. So you get 0.2 times 20, and that gives us a force of 4 newtons. So I know what the numerical value of this is. This is now 4 newtons. And that makes sense as to why this thing is accelerating to the right. But when I look at this, let's go back and look at the numerical value of this. It's 4 newtons as well, because it has to be according to the third law. Now, whether or not this makes conceptual sense, well, we said a net force of 4 newtons causes this to accelerate at 20. Let's take a look at the forces here. You got 8 newtons to the right, 4 newtons to the left. That's a combined force of 4 newtons to the right. So this has also a net force of 4 newtons to the right after you add up these two vectors, and that would give you the same acceleration. So now hopefully everything makes conceptual sense. However, let's say you didn't know the third law, you can actually still determine this force mathematically here. And in order to do that, what I would do is I would again apply the second law, F net equals ma. But now I have two forces, so my F net isn't just, we don't just pick a force here. We look at both of them here. So I know one of them was 8 and it's directed to the right, so I make it positive. And the unknown F2 on 1 would be to the left, so I would make it negative. And then ma would be 0.2 times 20, and what we would get is 8 minus F on 2 is equal to that. Or excuse me, F2 on 1 is equal to that. So then that is 4, this is 8, this is our unknown. When we move that over there, you get F2 on 1 being positive. Then we can move the 4 over there, it would become negative. You get 8 minus 4, you get the 4 newtons. Exactly what we were looking for right there.